We are starting with Marco Zaccaria. You probably already know him. He's in the R&D department of HCC Europe in the architectural field. And he's going to talk about a really exciting topic, pattern glass, and how do you define the strength of it and in really like the fundamentals of the scientific ones. So Marco, the floor is yours.
Thank you. The pointers, yes. Thank you very much. So good morning, everyone. I hope you had a better night than mine. I guess I'm suffering a little bit of artificial jet lag or something. But I think the talk is kind of nice and relaxed with some formulas. So I'm gonna talk you through this. And it's about pattern glass. If you're here, probably you know what pattern glass is. But if not, pattern glass is basically what you see here. It's a type of glass that, due to the manufacturing process, the transparency tends to fade in favor of some privacy and to create some partitions or more creative spaces on the interior normally, but even for the exterior. So what the talk will be about is really try to identify what's the strength of pattern glass, because historically it was found that despite being tested in the past, there were really no records to back up what's the strength of pattern glass. So we needed to do a little bit of a refresh at scientific and standardization level. And so we had a look on how the design standard today account for pattern glass strength. And then we went into an experimental work which consisted of 3 parts. First, understanding what's the topography of pattern glass, so really what's the surface profile of this glass. And then we did clearly destructive tests from which we could gather the data that are needed for the standard. And then we went together with some finite element analysis to see how all the study could correlate, and so that our conclusion could be quite strong. And I can anticipate some conclusions here already, so to put you in the mood, that the strength is highly affected by the stress concentration, which is induced by the geometry of the pattern. And then in second place, also, what is the effective thickness that is actually resisting the actions? And so these are the 2 main parameters that affect that. And I take the opportunity also to mention that this study that I'm presenting, it was a good collaboration with a colleague, which is Anna Shikinova, and she's at the forefront of the standardization committee. So she represents AGC when we go to the standardization committee, and to Professor Jens Nielsen, who was a professor at DTU in Denmark, and now he moved to new paths. So that was a really nice collaboration. So at every step, there are inputs by the others. So pattern glass, you saw some pictures before. I put some more pictures here because these are actually the patterns type that I'm going to talk through. Commercially, there is a very wide range of pattern glass available. So what we have here, it's a selection. Why we selected these? So if you see up there, Creepy is a pattern whose texture is 3D, I would say, or at least 2D, in the sense that it's not homogeneous, it's kind of random. We create this pattern a little bit fuzzy. And then, but the depth of the pattern imprinted is only 0.2 millimeters. So very little imprinting, almost negligible, let's say within the tolerances of a product standard. If you take the Niagara instead on the bottom, that's another type where the depth of the pattern is as high as 1.7 millimeters. So that's a really big depth. And you see it's very irregular, so it goes everywhere. And then we have 2 more, and for these 2 is where we run the finite element analysis, where the pattern is monodirectional and their depth changes, but this is somewhere in the middle. How pattern glass is produced? Well, this is not float glass produced. It comes from the roll cast process. That means you got the tank of melt material, and then it gets it's kept at a temperature of about 1000 degrees, normally 1050 maybe, and then it gets squeezed between the rollers. Normally you might have both rollers who have the cast imprint, so the imprinting could be on both sides, but more regularly, the imprint is only on one side only. And so after the cast, then it's normally rolled up, and then we have the usual annealing process that is kind of common for all glass. So if you go here now on this general figure, that's something that could start to be interesting and relevant for what I'm going to discuss about, because the question is what the thickness of patterned glass. So if you go to the standard will tell us that the thickness is the maximum. With Anna, we were discussing, shall we call it nominal thickness? Is it maximum thickness? For simplicity, I call it nominal thickness, but what I mean here is really that this is the peak-to-peak thickness that we are considering. And then there is also what I call the minimum thickness, is that if you take off all these pits and ridges of the glass, well, that's the minimum thickness. So what we assume that this was an ideally rectangular cross-section that will actually work. So once we define this, let's have a look on the standard. These are the formulas, not that complicated, I'll guide you through. So this is the EN 16612, but is also considered into the Eurocode, and that's where we think this work could actually start to take place. Because when we have the characteristic bending stress of glass, which we know is around 45 megapascals, then you will have to use some factors to go from the characteristic to the design strength. And if you see this factor here, which is the KSP, that is called surface profile factor. What does it mean? That depending on how the surface is on your glass, you have to apply a factor to take into account these surface changes. If we consider then pattern glass, we could say that taking only those three elements, so characteristic bending failure, FGK, then KSP and KE, which is the edge factor, we would be able to define the nominal strength of pattern glass. So the equivalent of 45 megapascal for float glass, what this is for pattern glass. And we get to the value of 27. Why? Because the standard tells us that this is 0.75, and if we are considering ASCAP edge, which what we did in this study, this will be 0.8. So just some maths gives you the 27. And so I showed you before how the pattern changes, and the surface profile is only one value, and this is 0.75, and that's probably where one of the problem is. So in the study, what we had to do, we had to test the glass and then verify that whatever we test had to be higher than this value, because if this was lower, it means that when we calculate the stresses for the standard, we are not into the safety conditions. So we started to question, this glass is not a homogeneous element flat like with a float glass normally is, what it is. There are some pits and ridges, and so the model for assessing this is like if you have an infinite beam where there might be a hole in it. But let's say there are several researchers who have studied different conditions, and each one will be different. We have 4 patterns. For each pattern, we will have a specific model like that type. So it will be kind of demanding going into all this analytical solution every time. And then the other thing is to consider how the actual thickness might be affecting. So we saw the Niagara has a 1.7 depth of pattern. That means if its nominal thickness is 5 millimeters, we will be here. For a given load, its stress will be a little bit less than 20. But if we consider that there is this depth of failure, so if we would calculate the stress by considering the minimum thickness, that would be with 1.7 millimeters less. So we will be here in terms of thickness, and you will see that the stress is almost double. So which thickness we should take into account when we do the calculations? So with this kind of hints in mind and things that we wanted to address, we started to do the study. So the study is organized into doing some surface topography, so really trying to measure what the patterns look like so that we can then model it for a finite element analysis. Then destructive test. This is quite standard, so done according to the EN 1288, so 1.1 meters panels. In our case, we test pushing upwards to take off the self-weight to rule out the self-weight of the glass. And then some finite element analysis that will reveal where the stress concentrations are. So the study was done on 4 commercially available patterns, which are the one that I show in the earlier pictures, and the test method was not consistent for all the 4 series. So the one where we went up to the finite element analysis are only the flute and the ray wall, simply because these are monodirectional, so easier to model and already easier to get some conclusions out of it. And then for the crepey, we didn't do the finite element analysis, but yet we tested with the pattern intention. And then with the Niagara, we also pushed a little bit for the as cut and ground edges, and also testing with the pattern intention and in compression. Today, I will not show you all these results because probably will mainly drive you out of what really the topic is. But there is the paper, so for those who are interested, hopefully it gets accepted and published, but I submitted for the Glass Structures and Engineering Journal, so at some point might be published there, and the full data will be available there. After doing the 4-point bending, we've done the Weibull analysis, and in this Weibull analysis, the calculation was done using the nominal thickness, as the current standard tells us, but also seeing what if we calculate according to the minimum thickness. And then the finite element analysis was made taking 2D plane stress parametrically, varying the thickness from 3 to 9 millimeters, and then triangular elements with second order displacements were considered. Big table, not to show you stuff here, I will focus better in later on, but to tell you all the parameters that are relevant there, which is the Weibull theta, so the 63%, which is kind of value of the average, not quite, but let's say, let me pass this. Then there is the slope of the best fit line, and then the goodness of fit, and then a characteristic bending failure. And this is also important for us to address the data, which is the ratio. So how many samples out of the batch that we tested are valid data? That means they either they failed within the loading ring, or they can be considered valid value. And then the radius of curvature, this is coming from the topography, radius of curvature of the pattern, so the minimum, and then the depth of the pattern. And again, calculation done twice because we were using nominal thickness and minimum thickness. So now I'm going to zoom in into some of these data. So we had 27 megapascal as our nominal value in first place. How do the tests compare with that 27? Well, you see, we want to satisfy this equation, and for 3 patterns, we couldn't satisfy this. Only the fluid pattern was doing well. So, in first place, what are the conclusions? The KSP, which will be here, varies much more than 0.75. So this value of 0.75 maybe could be an average out of there or something similar. I don't know. I didn't work out the average there, but clearly it's not representative of what's actually going on. And only the fluid series actually fulfill that. And then there you see a little bit the Weibull and how it works also somehow, how the data point distributes along the best fit line. So let's try to understand a little bit more what's actually is going on. So if we take the Weibull T pattern, you will see that the area of stress concentration is very limited on the pattern itself. So fractography done after showed us that 77% of the failure started from that point. So it's really the stress concentration which is playing a role there. And as a matter of fact, you see that the Weibull T is probably the weakest, and its radius is one of the lowest down there. If we do the calculation according to the minimum thickness, one more word here. There is also a tendency, yeah? If we compare the radius of curvature, all those who have a very low value, so these two, for example, the strength is 16, almost 16 and 19, so they are similar there. Then as the radius increases, also the strength increases, and as the radius increases, also the strength increases. So this radius is very large. You see, it's like almost 2 orders of magnitudes, 2 orders versus this, 1 order of magnitude higher than that. So this feels like very close to standard glass, or that 0.75 can work, but these others we are out. So that's clearly, we can say that the radius of curvature of the pattern is what playing most of the role. But is it the only one? Let's have a look on calculating the minimum thickness. And for me, the focus should really be on these two here, the crepey and the Weibull T. What happens? Well, allow me engineering-wise that 0.38 and 0.4 is the same value, or very similar, right? And you see now that the data there were a little bit further when we were considering the nominal thickness, but when we consider the effective thickness, those data tend to get a little bit closer. So in a way, even the minimum thickness is playing a role there. So this is something that should be taken into account. Now, up to which point this has to be taken into account? Let's see, the conclusion. The 0.75 fails to account for the variability of all the commercially available pattern glass. So this is something that probably the standard should take into account to address this best. We know that the strength is influenced mainly by the radius of curvature of the pits of the pattern. That's also very clear out of this study. And also the effective resisting thickness is playing a role. Now, given this job is serving standards, up to which point this second conclusion is important, I think that standardization has also the role to simplify the work of the specifiers. So maybe the secondary effect is something that could be embedded somehow into safety factors and to other factors somewhere. So where the work has to be done and addressed, it's really on this first part. And so after this study, we hope that this will serve the scientific community as well as the standardization community to take this into account and adjust or direct this new glass Eurocode, which will come into place shortly and will be complete with this part. Thank you very much for your attention.